And I got problem 74 for the first problem, which is basically showing you the diesel cycle, and we're going to find the pressure, volume, and temperature for each of these for 4 corners here, from 1 to 2, 2 to 3, and 3 to 4. So this whole thing is explaining, you could pause, read it if you want. It's really long, so I'm not going to read it. It's just explaining the difference between the diesel cycle and the Otto cycle. The only really thing you have to look at, because unless you really want to know, which is here, you're going to have the ignition is when it's at constant pressure from 2 to 3, as opposed to here where the ignition happens in the air and the heat enters at from 2 to 3, where it's a constant pressure, so it's an isobaric process. Anyway, so the only thing you really want to note is that the engine operates with intake air, squiggly Y thing, 1.4 at 25 degrees Celsius and 1 atmospheric pressure. The quantity of fuel injected into the cylinder has a heat of combustion of 1000 joules, so that'll be like your QH. Anyways, so now we're going to solve for the first part, right? So it's already given you all the values, as it says right here. The engine operates with intake air, 1.4 at 25 degrees Celsius and 1 atmospheric pressure. So at 1 atmospheric pressure, the temperature is 25 degrees Celsius, and you're also given the volume. So it's 1 atmosphere, 1050 centimeters cubed, and 25 degrees Celsius. However, we do have to do conversions. I'm not going to show you guys how to do, I'm not going to show you guys the exact conversions, because you guys should know how to do conversions, but these are how you convert. You're going to convert centimeters cubed to meters cubed for volume, atmosphere to Pascal for pressure, degrees Celsius to Kelvin for temperature. Anyways, so now we're going to do corner 2, right? So corner 2 is during an adiabatic process. So it's not just pressure 1, volume 1 is equal to P2, V2. It's P1, B1 to the air intake squiggly thing. It's equal to P2, V2 to the air intake squiggly thing. And so now you're just going to solve for pressure 2, because you already know volume 2, since it's given right there. It's 50 centimeters cubed, or 50 times 10 to the negative 6 meters cubed. So you're just going to plug in your values like I did here, and then you should get 7.19, or like 7 million, whatever. So it's 7.19 times 10 to the 6 pascals. So now you have to solve for T. Notice that when you're going to have to use the PV equals nRT equation for the ideal gas law. So you're going to rearrange to get T, which is this. So you should already know R, which is 8.314, but how do we know N? You're going to find N by plugging in your P1, B1, and your T1. So you're going to use PV equals nRT for the first corner to find N. You're going to plug in your values. I won't show you what they are because you should know them by now. It should be 0.043 moles. So knowing that, you're going to just plug in your values. Everything you should get at 1006 Kelvin. So then that should be your table right now. One for 1 and 2. And now we're going to go to corner 3. So corner 3 should be, you can have constant pressure, so it's isobaric, right? Because that's when the heat's entering and the pressure is constant. So then your P2 is equal to your P3, so your pressure is like 7.19 times 10 to the 6th. So like I said earlier, your QH is going to be 1000 joules here. And then and then here you're going to have to do the equation for how do you find, for finding QH. Because you want to find T3, so your temperature at 3. So it's going to rearrange that to get this. T3 is equal to QH over N times CP. Again, so if you don't know what CP is, it's right here, CP, because this is a diatomic gas, so it should be 7 over 2 times your R, so your which is 8.314. Sorry, I blanked out, I forgot what the R is. So all that plus your temperature at 2, so you're going to get 1000 joules times N times that, which should be 29.1 when you do that. You get 1805 Kelvin for your temperature. So what's your volume? Again, you're going to use PV equals nRT, but with all your values that you got for 3 so far. I'm not going to show the values because you should just know them. So you're just going to plug in your values. You're going to get 8.97 times 10 to the negative 5th meters cubed. Now for the fourth one, you're gonna have constant volume. So your volume is gonna be the same as it was for this part. Also, it's 1000 so 1050 cubic centimeters, and it's an adiabatic process. So we're gonna do the same thing we did for the second one, which is P3V3 is equal to the 1.4 is equal to P4V4 to the 1.4, because 1.4 is the air intake value. So then you're just gonna solve for P4, plug in your values, and then you should get 229,500 pascals for your third pressure. And then PV equals nRT, T equals all that stuff. Just plug in all your values, you get 674 Kelvin. And then how's it different from the Carnot cycle? So this is what the Carnot cycle is. And then, so Carnot cycle, you're starting out from 1 to 2. You're doing an isothermal compression, an adiabatic compression, and then an isothermal expansion, and then an adiabatic expansion. So like that's the order of things, how you're doing it. But for the diesel, you're, again, notice how you have no spark plug or anything. You're just doing an adiabatic compression, an isobaric expansion, an adiabatic expansion, and then the isochloric process, or it's constant volume. So those are the differences. So like they might look similar, but they're not. And then you also, so the heat intake's coming in from here at the top, from 1 to 2, and then it's leaving from 3 to 4. And that's kind of it. So anything tricky? No, not really. Just almost forgetting that it's not just P1V1 equal to P2V2 when you're doing 2 and 4. You have to include the air intake because it's an adiabatic process. That's kind of it. So thank you. If you have a diesel truck, yeehaw, vroom vroom. This problem is kind of for you, I guess. All right, thank you.